Hi, I'm Androutsopoulos. I am professor of AI in the Department of Informatics, Athens University of Economics and Business, where I also co-lead the natural language processing group. And I'm also a researcher at Archimedes, which is a research unit in the Athena Research Center. But I should also say that I have worked here at Demokritos for several years, and I actually owe a lot. Demokritos helped me a lot, and it is one of the reasons I came back to Greece. So I'll be talking about NLP, natural language processing, which means I'll be talking about systems that try to understand natural language text or to generate text. And you can also combine NLP with other technologies like speech processing, for example, to create systems that understand spoken dialogues, but I won't be talking much about speech or images here today. It will be mostly about written language text. What I'll try to do is I'll try to summarize the key ideas that over almost a decade have transformed NLP and have led to what is now known as large language models, or some people call them foundational models, possibly because they are now used also not only with text, but also with images and sound, all sorts of data. But again, in this talk, I'll try to take you all the way to LLMs, but by staying at text. So one of the key ideas in modern natural language processing is that we can represent each word of the vocabulary of a language as a point. For example, see these points here, which are, for example, company names or location names, etc. And we can do this in a way that, so that words that are related are close, and words that are not that much related, they are further apart. Okay, so you can see here that, for example, company names are all together, and locations, for example, or months, etc. Most of you will already know about vectors, or at least two-dimensional points. When you have two-dimensional points, each point is just two numbers. It's x and y coordinate. But these points, which represent words, have many more dimensions. So each word is represented as a point in our, say, 300-dimensional vector space. And we don't actually know what these numbers mean, right? They are hidden, they are latent pieces of information. So now you may start wondering, if these dots, each dot is 300 numbers, how on earth did you manage to plot them on this slide? And there are many ways to do this. One way is to use something like a mathematical funnel, right? So you take your 300-dimensional vector and you push it through this funnel, and you get a two-dimensional point that you can plot on this slide, right? So actually, this funnel is not really just a funnel, it's also a filter. So when you transform a 300-dimensional vector into just two numbers, it throws away information that is not that much important. It tries to filter to keep just the important information and give you a two-dimensional point, right? Now, mathematically speaking, this funnel is a multiplication with a matrix, right? So if you know about these things, you take your initial vector, you multiply it with a mathematical funnel, which is the matrix, and you get your new vector. Or in deep learning terminology, this is also called the dense layer. They all mean the same thing, right? So when people started using word embeddings a lot around 2012, 2013, immediately people were very much excited because they can capture lots of interesting pieces of information. So one interesting thing is, as we have seen, that you get dots, and dots for words that are related are very close together. Another interesting thing is that they capture analogy. So another famous example is this one here. So if you look at the dot for the word man and the dot for the word woman, and you connect them with this little arrow, or the pair uncle, aunt, or king and queen, all these arrows have approximately the same direction and the same length. So if you don't really know, if you don't know what is the English word for the female of king, you can take one of these arrows that connects man to woman or uncle to aunt, and you put its origin on king, and it will take you to the word which is queen. So you can sort of, solve questions like, what is to king, what woman is to man, right? And this, again, and other things got people excited with word embeddings. And there are lots of ways to create word embeddings. A very famous, widely used tool is called Word2Vec, but there are lots of other tools. So how does this Word2Vec tool work? Well, you need a very large corpus, a very large collection of plain text. It's plain text, not annotated. Think of things like Wikipedia, or all the books you managed to collect, all the English books you managed to collect online. And you concatenate all the, say, articles of Wikipedia. You create a very, very long plain text file. And let's say that we are at position T of this very long text file. So the, say, 1 millionth word of Wikipedia is, let's say, word film. And you look a few words on the right, say I could be 5. So you look 5 words to the right, and you see that there in Wikipedia you have the word famous, right? So you create 2 pairs. The green pair connects the word film that you have at position T, say position 1 million of Wikipedia, to the word, say, famous that you have 5 words to the right. And this is the correct pair, the green pair. And you also create another imaginary pair by just sampling a word from your vocabulary. Let's say you pick randomly a word, and let's say it's medical, the word medical. And you create another pair that connects film to medical, right? So what you do then is you move a bit closer the points for the words of the green pair, you move film a bit closer to famous, and you move the words of the red pair a bit further apart, right? You move them, you increase a bit their distance. And you do this millions and millions of times until you create your word embeddings. So this text box here just summarizes things we have said. Again, I'm hiding lots of details, but that's the key idea, right? And as I said, this got people very, very excited, but then immediately people also started pointing out, finding various disadvantages of word embeddings. One problem, I'm sorry, you can't read these words, but I'll tell you what the slide says. Most words have multiple senses, right? So, for example, here, where I'm pointing, says *2. It means that it's the second sense. If you open a dictionary, it will be, let's say, sense number 2 of the word star. And the words nearby are things like planet and asteroid. This is the space sense of star. But there's also another star here. It says *1, and its nearby words are things like television, video. This is the Hollywood star, okay? And there's also a Jaguar up there, which is next to convertible and luxury. It's the car manufacturer Jaguar. But there's another Jaguar here next to hunter, which is the animal sense, right? And another famous example is bank. Bank 1 is close to finance and transaction. This is the financial sense of bank. But there's also another bank here, which is the river sense of bank, ochthi in Greek, which is close to geographical terms, right? So because each word has multiple senses, but we only have one vector, one point, one word embedding for all the senses of a word, we're in trouble. So for example, in the case of bank, Word2Vec will create a word embedding that will be somewhere in the middle, which captures badly both senses, right? So, and some people try to create extensions of things like Word2Vec to create one point for each sense, but nowadays we don't really use these methods, so we still produce a single word embedding for each word. And what do? Well, we start with, say, a generic embedding of bank, which would be somewhere in the middle between the financial and the geographical sense of bank, but we hope that our neural networks will adjust these points by looking at the context. So if I'm inside a text with lots of financial terms, then I hope that my neural network will revise the word embedding of bank to move it closer to the financial sense, right? And how do we do these revisions, this kind of revision? I'll tell you in a moment. So these things we have already covered. So one way to revise your word embeddings, let's say that we start with a sentence that has n words, and one of the words is bank, right? Let's say it's word number 3. Well, it will be the word2vec will give you the generic bank embedding, which will be somewhere in the middle between the financial sense and the geographical sense, and it's terrible for both senses, right? So what we do is we do revisions, and for a long time, up until 2017, 2018, the state of the art to do revisions of this kind in NLP was recurrent neural networks, RNNs, and actually stacked RNNs. I'm not going into any details about RNN, I'll just tell you the key ideas. So what happens here, the E1, E2, etc., are the initial generic embeddings that word2vec will give you, and these H1, H2, H3 are, you can think of them as revised versions. So you still have one vector, one word embedding for each word of your input sentence, but it has been revised. So you hope that if the third word is bank, and if you see lots of financial words around, you hope that your neural network will have revised H3 to move it closer to the financial sense. And an RNN, actually a bidirectional RNN, does this by looking to the words on its left and right, which is why I'm drawing these bidirectional arrows, right? And having revised your word embeddings, you do another revision. This 2 in brackets means second revision layer. And then you can stack lots of revision layers. These are stacked bidirectional RNNs. And at the top layer, say layer capital L, you will still have a vector, you will still have a word embedding for each one of your words of your input sentence. But you hope that these will be much more context aware, as we say. So they will have been moved towards their correct senses. And actually, this is actually a simplification because these revision layers don't just make the word embeddings more context aware. Another thing that they do is that they transform your word embeddings to make them better for the particular application you are targeting, right? So the generic word embeddings may contain lots of uninteresting information for a particular task that you are trying to solve. For example, if E3 is a verb, the word embedding may also contain information telling you if it is a transitive verb, if it requires an object, or if it's an intransitive. Or if it's a noun, it may contain information like, you know, if it is made of wood or made of iron, things that you may not care about in a particular task. So as you move from the lower to the upper revision layers, the embeddings become more context aware, but they are also becoming better tuned to the particular application that you are trying to address. Let's see an example. One of the things we've done in our group is trying to extract information from legal text, so in this case, contracts. So you have a contract, an agreement between two companies or between persons. And in this case, you need to do not text classification, you need to do token classification. So for each word of the text, you have to decide if the particular word is part of, say, a contractor name. So for example, here it says, sugar 13 ink. For sugar, for 13, for ink, you need to place those tokens in the class part of contractor name. And there are also classes like, here it says October 16, 2014. You have to place all these 3 tokens in the class termination date because it says here to be terminated, which is again an example of why they need to be context aware, these embeddings, right? So we're trying to predict start and end dates, durations, contractor names, etc. And all the other words, which are not shown in yellow, should go into the category in the class other, nothing, okay? So how would you solve this task? Well, you can so you can process, let's say, sentence by sentence, and for each sentence, you start with the initial generic embeddings that word2vec would give you, and then you do lots of revision layers using stacked bidirectional RNN until you arrive at the top revision layer. And then how would you get the opinion of your system about the class of the first token? Is it a person? Is it a location? Let's say that let's assume we have only these 4 categories: person, location, organization, or other. Well, what you would do is you would take the top level embedding for the first word of the sentence, and you would pass it through your mathematical funnel filter, and you would set your filter to create only 4 numbers, right? So your embedding may be, let's say, 300 numbers, but you pass your 300 numbers through a funnel, and you get only 4. And I should also say that these funnels, they also have another gadget at their end, which is called an activation function. You'll probably hear about activation functions in other lectures as well, but in our case, what this thing here does, which is, it's called a softmax in this particular case, it makes sure that the 4 numbers that you get look like a probability distribution. So they have to be between 0 and 1, and they have to sum to 1, right? And this is what the dense, again, is the funnel, and softmax is this little gadget at the end, the activation function. So my system thinks that there's a 0.75 probability that this is a person, 0.05 that is a location, and so on. And I do the same, using the same funnel on top of every one of the top revised embeddings of my sentence, and this way I get a probability distribution for each one of the words of the sentence. But because we're doing supervised learning, we also know the correct distribution. The correct distribution would be, as we say, one hot. It would give all the probability mass to the correct class. So what I'm going to do is I will compare the distribution that I output for the first word to the correct one, which is one hot, and I will do the same for the second word and the third word. And the way to do this is to compute what is called the categorical cross-entropy loss. So you get a loss, an indication of how well you did for each one of the words of the sentence. You then add these losses, and you get a single loss for the entire sentence, and you use the single loss to do backpropagation. And the backpropagation, what it does is it updates all the numbers of the mathematical funnels, not just this one here, but all the other weights of the neural network below. But how would you address a task where you have to do text classification? There are cases where you don't need a decision for each word of the text, but you need a decision for the entire text. A fun application we have worked on in my team is trying to help moderators of social media. You probably know already that, in social media or in discussion fora of newspapers, discussions often get wild and people start using, bad words. You get racist comments and so on. We call these comments toxic. And all the big social networks, they have tens of thousands of human moderators trying to filter out the toxic, the bad posts. And this is a distribution of how many posts we had online just from a Greek sports newspaper, right? So imagine if you are a much bigger network. So you can't do this by hand. So we and others have developed methods that try to help the moderators. So for each user post, the network produces a number. Here it says 85% probability of being toxic. Here it says 0% probability of being toxic. So what you could do is for the posts that the network thinks are very, very innocent, very green, you just let them pass. For the posts that the network thinks are very toxic, you just reject them. And you let your moderators handle the gray zone, for example. There are lots of things you could do. And we also want to help the moderator by creating heat maps, like this one here. So here, for the last post, the system thinks that there's a very high probability that the post is toxic, and we also get this heat map. Here, the deep red is the bad word, yourself, right, or ignorant vandal. So it shows in red words that make it think that they are toxic, right? We do this using attention scores. It's just one of the many ways you can do to sort of justify decisions of your network. It's probably not the best way. I'm just mentioning it as an example of trying to explain the decisions of your system. And it's important that the training data for each training post only have the correct label. Was it toxic or was it not toxic? They don't have these annotations. They don't tell you where the bad words are. So you get the heat maps for free without your annotators having annotated toxic spans, right? So how could you do this? Well, when we did this first version of this work, we were only using a unidirectional RNN, not even stacked, because it was back in 2017 and our GPU cards were very small. But now that you know about stacked RNNs, you can imagine that, okay, here you have a post. Let's say I tweet. It says, hello there, friend, I don't know, relax. And now that you know about stacked by RNNs, you can imagine that you start with the generic word embeddings of the words of your post, and you revise, and you take the high level, the top level word embeddings, which are these things here, the h1, h2, up to hk. Now, but this way you have a vector for each word of your text. We need a vector for the entire text to be able to decide about the category of the text. So the simplest thing you could do would be to just add the vectors of the words, the revised vectors of the words, and just divide by their number. This would give you the centroid. The centroid is, in fact, a point in the middle of all the points of the words of your sentence, right? But can anybody think of a reason why this is not a very good strategy? So I have a point for each one of the words of my post, and because I need a single vector, I just add them and divide by their number, and this is the centroid, yeah?
Words that are not of much significance.
Right. This way, when you compute the centroid, you assign equal importance to words that are, bad words, and also articles of prepositions, which you don't really care about in this particular application. So you need something, when you sum the vectors of your words, you want to multiply each one by some number, alpha 1, alpha 2, up to alpha k, which will be a number between 0 and 1, and we want this alpha number to be high, to be almost 1, for words that are very important, and almost 0 for words that we need to ignore when computing the centroid. And the fun fact about this network is that even the alpha scores are produced by the network itself. How do we do this? Well, to compute the alpha score for the first word, we take the top revised embedding of the first word, and we pass it through a mathematical funnel again, which we adjust to make it output just one number. And this one number is the alpha score of the first word. And then we take the top layer revised embedding of the second word, we pass it through the funnel, and we get alpha 2. And then we pass all these alphas through a softmax to make sure that they are a probability distribution. And so we compute a weighted sum of the revised embeddings of the words of the text, and then we pass this this single vector, which represents the entire text, through, again, a funnel. If you have only 2 categories, this funnel could produce just 2 numbers. If you had 4 categories, 4 classes, this final mathematical funnel would produce 4 numbers, and with a softmax, they would again be probability distribution over your 4 classes. And again, because we do supervised learning, I'm just skipping some details. Because we're doing supervised learning, we can compare the output that you produce to the gold output, which would be, again, a one-hot probability distribution, and you would get a loss, and you would backpropagate to adjust all the weights of your neural network. And this is how it works if you have an entire text to classify. And the heat map that I showed uses the alpha scores. So the words that are shown in deep red, they had a very large alpha score. In cases where the post was innocent, we were seeing an almost flat color over all the words, even though softmax tries to push one of the numbers to be larger than the other ones. Okay. So interestingly, this was the state of the art using bidirectional stacked RNNs up until 2017, 2018, when transformers appeared. And then, well, actually, to be honest, briefly, people were also trying to use CNNs. You may hear about CNNs, convolutional neural networks with text. You can do it, and they work, they are faster. But then transformers came out, and everybody started using transformers, even though RNNs are still very interesting, and there are recent papers that try to combine ideas from RNNs and CNNs and also transformers. For example, RNNs, if you do language modeling, I'll talk about it later on, at inference time you have linear, actually constant complexity, whereas transformers have squared complexity when you use them as language models. So there are still advantages of RNNs, and people try to combine ideas from different types of models, but from 2018 and until today, transformers dominate, right? So I'm going to talk about transformers a bit. The main idea is very, very similar. If you have an input sentence of, say, n words, well, I should actually say transformers don't use tokens that correspond to words. They use subword tokenizers. So the tokens of the transformers may correspond to parts of words. So if you have a word like replaying, you may have a separate token for re and play and ing. They're not that linguistically motivated, the subwords, as I make it sound. They're not, but this is the key idea. You break long words that you haven't seen that many times into smaller parts. But let's forget about this, and let's assume that all the X's are the initial word embeddings of the words of your input sentence. And again, you have multiple revision layers. Revision layer 1, 2, 3, 4. You can stack as many revision layers as you like. The difference is that when, for example, you're here computing the revised vector for the second word of your text, you actually sum all the vectors of the words of the text from the previous layer. But you don't just sum them, you again multiply each one of them by an attention score. So it's like, imagine that this guy here, H2 revision layer 1, is asking all those guys from the previous layer. So, hey, I'm at position 2 in the revision layer 1. I'm asking X1, how important are you to me? Okay, how useful are you to me? So this alpha 2-1 means for the position 2 of the revision layer, how important is position 1 from the previous layer? And similarly, alpha 2 means for the revised position 2, how important are you, X2, in the previous layer? Up until 2n, alpha 2n means, okay, I'm trying to create the revised vector for position 2. How important are you, the vector at position n from the previous layer? So again, you sum them all, but you multiply the x's by the corresponding attention scores. That's what this summation here is doing. And then you pass this weighted sum vector through an MLP is actually multiple mathematical funnels, one after the other, right? And you adjust the funnels of this MLP so that you will get another revised vector with the same dimensionality typically as the initial vectors. Right? And you do this in all the revision layers. In all the revision layers, this is the formula you use. So to produce the new vector for position 5, but now you add the vectors from revision layer 1, right? So you add the vectors of the previous revision layer, multiplying each one by the corresponding attention score, okay? And now, to avoid getting into details, I won't tell you how these alpha scores are computed. There are extra slides. I will distribute my slides. If you want to see how these alpha scores get computed, they get computed by the network itself, but I'm not going into these details, okay? So now, if you wanted again to do token classification, imagine again that we have contracts and we need to classify each word of the contract into the correct category. Again, I will just take the top revised embedding for the first word of my contract. I would pass it through a mathematical funnel, a dense layer matrix, which would output 4 numbers, one for each one of my classes. And again, I would use a softmax if it's a single label classification problem. Again, nothing else changes here at the top. I would get a distribution, probability distribution for each one of the words of my input. I would compute a categorical cross-entropy loss, which tells me how close the probability distribution, say for the first word, the probability distribution I produced is to the correct one, and similarly for all the other words. I would sum the losses, and I would get a single loss for the entire sentence, and then I would do backpropagation. And then I would feed the next training sentence. Actually, we work with mini batches, as you can imagine. We don't feed a single sentence at a time. We may feed, I don't know, 64 at a time, right? So this is what this slide is showing. Now, if you have a task like text classification for moderation, where you need to classify an entire text, not each word of the text, well, you could again do what we did with the RNNs before. But what is more common is to just do what is called a max pooling operator. So again, you take the top revised word embeddings, and remember, these are vectors, right? So you go and look at the first dimension of all these top vectors, and you keep the maximum. Then you go and look into the second dimension of all these vectors, and you keep the maximum, right? And this way you get a single vector which contains the maximum number of each dimension over all the words of the text. And this way, again, you get a single vector, and you pass it through a funnel, which you make sure it outputs as many numbers as your classes, and again, you do backpropagation. So now I should say that I'm hiding lots of details. So if you already know about transformers, you will know, for example, that transformers typically have multiple attention heads. What is an attention head? What does it mean, multiple attention heads? Well, it means that, for example, when you are here computing the revised vector for position number 3, well, you actually, if you have 10 attention heads, you get 10 new revised vectors, and then you combine them to get a single one, right? So multiple attention heads means that for each new vector, you initially get multiple candidates, and then you combine them and get a single one, right? And I'm also hiding things like how the alpha scores are computed, or of course you use things like dropout or layer normalization or residuals and all these things that you will probably hear in other lectures in this school. So this brings us to BERT. BERT came out around 2018, and it was a big revolution because it was, in NLP at least, one of the very first successful models that was pre-trained. What does pre-training mean? Well, first of all, what do you have inside this BERT box? Well, hiding again several details, the BERT box inside has these multiple revision layers. So it's multiple transformer revision layers. I'll show you here. So how do you train it? You get sentences from, let's say, Wikipedia or from all the English solutions you select, and for each sentence, you get names of word embeddings, right? And then the revision layers inside your BERT will revise all the embeddings of the words of your sentence, and at the top level, you will get the revised embeddings, normalized for each word of your input. So you feed a sentence into BERT, and you can get a revised vector for each word of the sentence. But how do you train it? Okay. So the trick is that we want to use lots of examples without paying human annotations. If you have a very large neural network like BERT, it has millions or billions of weights. You can't just use 100 examples. You need many examples. You cannot ask human annotators because those take a lot of money and don't have to. Without paying human annotators. So what do? We get each sentence, say, of Wikipedia, and we mask, let's say, one word. Here we had the word improvisation, we mask it, right? Now, although this word is hidden, in the revision layers of BERT, inside the revision layers, let's say that the third word is hidden, but still you will get a revised vector at the top layer for the third word, even though it was masked, because it looks at the context, right? So even though it doesn't really know which word you had here at x3, it can still produce a revised vector for h3 at level 4 because it looks at all the context, right? So we ask BERT to, if we have hidden, say, word 5, we ask BERT to use the top level revised word embedding of word number 5, and using that word to predict which word we masked. How do we do this? We get the top level embedding of word 5, and we pass it again through a mathematical funnel. Actually, I should show it like this, because it will create many more numbers this time. How many numbers? Can anybody guess? Let's say that the top embedding is 300 numbers, right? I take the top level embedding of word at the position 5. How many numbers do I need to generate, to squeeze out of these 300 numbers? Yeah?
As many words we have?
As many as the size of the vocabulary, right? We need a number for each word in our vocabulary. If your language has, say, 100,000 words, 100,000 numbers, right? And again, with a softmax, we'll make sure that they look like a probability, and we will compare this probability that the model generated to the correct probability, which will be one hot. It will have all the probability mass at the position of the word that we mask. And actually, we don't mask only one word. We mask approximately 15% of the tokens. So you get multiple losses, one for each word position that you mask, and you add these losses and you backpropagate. And you can do this for millions and millions and millions of sentences, right? And this way, Google and many others have trained BERT-like models, right? And the trick is that you have many training examples without paying any human annotators. But hold on. This system is trained to do something that we don't really care about, right? What can it do? You give it a sentence, you mask a few words, and it guesses the words that you masked. But who cares? Well, actually, some people care. We had a Nature paper where we did something similar with ancient inscriptions. So you have ancient texts on pieces of marble, and some words or letters are missing. And we were we were trying to recover the missing words and other things. We were also trying to date the inscription and find the location it comes from and so on, right? So actually, it is not, some people care about this task, but most people don't really care about this task. So what is the trick? You pre-train BERT to do this task for which you can find millions and millions of examples for free, and then you do some additional little training to tailor your BERT model to a task that you really care for. So for example, if what you want to do is, again, think of the contracts again. You want to classify each token as person, location, organization, or nothing. Actually, this B means beginning of person. Usually you have a separate class for the beginning of a person name, another class, it's called inside, for all the other words of a person name. And this way, if you have one word, one name after the other, you can tell where one name stops and the other begins. So let's say that you had, again, just 5 classes. How would you do this? Well, you would pay your annotators to create a few, let's say 300, 400, a few hundreds of training examples for the problem that you care. And then for the first word of your, this is the first word, and the correct class is O, outside, nothing. Okay, you take the top-level revised embedding, and you pass it through a funnel, which gives you as many numbers as your classes, right? So what you have done is you took BERT, pre-trained, and you just added a custom, a task-specific funnel on top of each word, right? And then you do some fine-tuning. So you train BERT with the extra funnels on top for your particular problem on the few hundred of training examples that you have. And this is called fine-tuning. So you start with a pre-trained model, and you fine-tune it, you further train it with some task-specific component on top on a few hundred, say, of examples that you have for this particular task. And it works much, much better, because probably during its pre-training, BERT has learned lots of stuff about this particular language and also common sense knowledge about the world this text comes from. In a similar manner, if you wanted to do text classification, then you would take a pre-trained BERT and you would annotate a few hundreds of texts, each one with the correct class. You would pay human annotators to create a few hundreds of training examples. And then in this case, because we want to do text classification, usually at the beginning of each sentence, we have a pseudo-token called CLS from classification, right? And when we try to predict something about the entire sentence, we take the top-level embedding of this pseudo-token, the CLS token. We pass it through a funnel. If you had 10 classes, your funnel would produce 10 numbers, one number for each class, with a softmax again, and you would further train your model on the few hundreds of examples that you have for the particular problem that you care about. So again, get a pre-trained model, add some task-specific component on top of it, in this case on top of the top revised embedding of the CLS token, and jointly train your BERT with the custom funnel on top of it, pre-train it on a few hundreds of examples that you have paid your annotators to create. And this, again, works much, much better. You can also do machine translation using transformers. This is probably what happens when you use things like Google Translate. So in this case, you have a stack of encoders. These stacked encoders are again these revision layers that we were talking about, right? So multiple transformer revision layers, these are the encoder blocks. And in this case, you feed your encoder stack with a sentence that you want to translate. So you start with the initial word embeddings for these 3 French words, and the encoder stack revises and revises and revises these 3 vectors, these 3 embeddings. So at the top of your encoder stack, you would again get 3 vectors, each one for the each being a revised version of the corresponding French word. And we also have a decoder stack. The decoder blocks are similar, so they also do revisions, but they also have an additional component that allows them to also consult the vectors that the encoder produced at the top, right? So what happens here on the decoder side is you feed the decoder with the translation so far. Let's say that we have already produced the translation I am a, and now it is the time to produce student, right? So you feed the decoder stack with the initial word embeddings of I am a, and the decoder revises these vectors, and then from the top revised vector of the word a, it guesses the next word, right? So you would take the top revised vector for the word a, you would pass it through a funnel, probably this way, which would again produce a number for each word of the English vocabulary. And in the simplest case, you would greedily select the word with the highest probability. If this word is student, you will add student as the next word of your translation. And then you will feed the translation so far, again, at the bottom of the decoder, and you will predict the next word and the next word, right? So the decoder gets as input the translation so far, and using the revised top-level embeddings, it guesses the next word. But it also has these arrows that allow the decoder blocks to look at the vectors of the French sentence, right? So when you do translation, the decoder stack has 2 inputs. One is the top-level embeddings of the French words that we need to translate, and the other input is the translation so far. And what it does, it guesses the next word, and then the next word, and then the next word. So it produces the translation word by word. Does this make sense? And let me also tell you another fun thing is that you can use a very similar architecture to translate not from French to English, but from images to text. This is called image captioning. So you can have images like this one, a train, and the text, the caption, is not written by a human. It is generated by a neural network. In our team, we have been doing this with medical images. So you have things like X-rays, and you want to generate the text that your radiologist would produce as the central part of his or her diagnostic report. So what do they see, and is interesting in this particular image. So image captioning is very important if you want to help medical staff, or if you have eyesight problems. There are now applications that allow you to look through your mobile phone, and your mobile phone is telling you what is in front of you, right? Or if you want to do image retrieval, you can couple each image with the corresponding text, and we know much better methods to do search from keywords to text, right? So you can treat each image as a text instead of an image. Now, all this was using transformers, which is the technology of 2017, 2018, right? And what I'm trying to say is that I'm going to move on and tell you about GPT-3 and 4 and things like that, and Llama and all that. You should also keep in mind that, okay, again, omitting some details, these models, although everybody is talking now about them, they still use transformers. So what I'm trying to say is that in terms of neural network architecture, nothing has really changed since 2017, 2018, right? We still use transformers. Okay, again, I'm hiding some details. There are things like, if you know about these things, mixture of experts and or models that try to combine ideas from RNNs and transformers and CNNs, but still, all the main models out there still use transformers. So nothing has changed in the architecture and algorithms that we use. What has really changed is the data, the training data that we use, and how we train the models on the data, right? So behind ChatGPT, there was no terribly new architecture. It was just lots of data and some clever way of using training data that I'm going to talk about. So how do models like GPT-3, GPT 3.5, GPT-4, how do they work? Well, they delete the encoder stack. So remember, this figure was from the case we were trying to do machine translation. The input to our encoder stack was the French sentence we wanted to translate. The input to the decoder, actually there were two inputs. One was the translation so far. The other input from these diagonal arrows was the top layer embeddings of the French words that we need to translate, right? So GPT 3, 4, whatever models, they delete the encoder stack. So we are only left with a decoder stack, and the input to the decoder is not the translation so far. It is a piece of a text, let's say a sentence, right? So I'm telling you, decoder stack, here is an incomplete text. Please predict the next word, right? So what it does, the decoder stack, is it reads I am a, and using the top layer embedding of the word a, it predicts the next word. How does it do it? It creates a probability distribution for all the English words, and in the simplest case, you would greedily select the most probable word. You would add the most probable word to the end of the input, and you would then again tell your model, now generate the next word, and now the next word, and now the next word. So each time you predict the next word, you add it to the input, and you predict the next one. And so what they are actually trained to do is they are trained to do autocomplete, right? You give them a piece of text, and they try to guess the completion, the continuation of this text, right? But with these models, and actually this is how they were trained. So they were trained by giving them millions and millions of incomplete, say, sentences and asking them to complete. So they are trained to do autocomplete. But actually, the text that these models can autocomplete may not be just a piece of a sentence. It may be an entire dialogue. So very soon people started realizing that, hey, you can give to the decoder side a very long text of this form. Usually there is an introduction paragraph saying things like, oh, you are a polite, helpful bot. You try to help people. You always create polite response and so on. And then some description of the problem that you want the model to solve. That, hey, my model, I will be giving you questions and you should be telling me the answers, right? And then you very often provide some examples. These are called few-shot examples or in-context examples or demonstrators. So if I give you this question, the answer should be this. If I give you this question, the answer should be this, and so on. And now I'm giving you a question without the answer, and do what you know how to do, autocomplete. And of course, a very probable completion of a question is the answer. And very often they do produce the answer, right? So why is this so interesting? Because just by using a single model, we don't do any fine-tuning, right? So before these models, the state of the art is get something pre-trained like BERT, and then do additional fine-tuning on a few hundred examples that you have manually created for the task that you care about. And this way you would end up having a different fine-tuned model for each one of the tasks. So if you're a company and you want to serve dozens of tasks, you would have to use dozens of models, each one fine-tuned for the particular task. Now there's only one model, and you talk, if it's an OpenAI model, you talk with it through an API, and you just tell the model what you want to do, and it does it. There's no fine-tuning. Well, that was the initial promise. But it didn't always work that well, because very often you may give a question to the model, what is the capital of Greece? And you may get a response of this kind. Why, bad words, do you care? Because this is also a probable completion, isn't it? And many of these models have been trained on Reddit threads, which are full of toxic content and so on. And very often you may ask, who is the wife of Barack Obama? And instead of the response, you may get something, and when and where was he born? because that's also a probable completion, right? So these models that were just pre-trained to autocomplete were not always doing what we were asking them to do, or they were doing it in a rude way. So what made a big difference, and people all over the world started talking about ChatGPT, was that they did one more stage of training, which is called instruction tuning. Anyway, there are many different terms. What they did is they employed tens of thousands of people from around the world, and they told them, hey, each one of you, just create a request about anything. How do I go from Athens airport to Demokritos? How do I cook, I don't know, cookies or chicken or whatever you like? But you also need to provide the ideal answer, right? So they collected tens of thousands of queries about anything and the ideal response. And then they did additional tuning. So they start with a model which is pre-trained to just autocomplete, and then they do additional training to ensure that to make the model, when prompted, when given one of the requests of the human annotators, to produce something very close to the ideal answer, right? And this made a huge difference, and this is what made people crazy about ChatGPT. There was no other invention or change of architecture or whatever. It was just using additional training of this kind, okay, and also scaling up and having billions and billions of parameters. But hold on, then we are back to pre-training and fine-tune. Remember the initial promise that with these models you just need pre-training, no fine-tuning. Now we also need fine-tuning, but it's a different kind of fine-tuning. It's fine-tuning on requests about anything, not about a particular task, about any task you can imagine, right? And okay, to be honest, people also started using reinforcement learning. There will be a lecture about RL, I think, tomorrow. So you also ask your annotators to fill in forms like this one, telling them, please tell me if the response of the model was toxic, or if it actually replied to the question, or even compare, if you have two candidate answers, which one of them is better. So you ask your annotators or other models to rank candidate responses. And this way you get a reward signal, which you need reinforcement learning to use, because you get a stage which is not differentiable, right? I'm almost done. I just want to show you one more key idea that make also a difference. It's called chain of thought prompting. So with the models we had before this idea, if you ask them to do things like, read this little story and, hey, compute how many tennis balls now Roger has, the answer was wrong, right? Sorry, this is again a few shot example, and then given a new question, the answer was wrong. Now, we don't just provide the model with a few in-context examples, we also tell the model that, hey, we don't just want the answer, we want to tell us how you thought about the answer, right? So this is called a chain of thought string, and then the answer. And the model tries to mimic the examples that you gave it. So it produces something explaining how it generated the answer. So this improves the responses, and you also have some clue about how the model is thinking. Let me just say also that these models are trained on anything on the internet, and there's a lot of code on the internet. So in case you don't already know this, you can use things like Copilot if you're a programmer, and you write an initial part of your program, even just the initial comments saying what the rest of the code will do, and then you press tab or whatever, and it auto-completes not just a word, but dozens and dozens of code. But of course, you are responsible, right? So the code may look very, very professional, but it may, I don't know, it may be terrible in terms of security. You need to check it. And there are also models where you can ask the model, say to the model things like, hey, explain what this code does, or please debug my code, or please improve the style of my code, and so on. I'm running out of time, so I'll just mention two things very briefly. One which is very, very popular, it's called RAG, Retrieval Augmented Generation. You will probably have heard already that these models very often hallucinate. So they produce responses that are not true, right? And they generate text in a very convincing way, but what they're saying is simply not true. So there's a lot of work trying to combine a retrieval component with an LLM. So in this case, when you get a question from your user, you first do a retrieval. You retrieve relevant documents, say from documents that you trust, or paragraphs from those documents, and then you instruct your LLM. You tell it, oh, my dear LLM, here's a question. Here are paragraphs from documents I trust. Now, please generate your response, but please base your response on the documents that I retrieved. Don't just imagine the answer. And this often works much better, and this is a very active line of research. The last line of research I'm going to mention is agents. I will just show, to be brief, just a screenshot of my terminal. You can think of the retrieval component as just one tool that these models are allowed to use. So you may tell your model that, hey, you can also use a model that generates text from images, or a model, another tool that captions images, or, sorry, what did I say? Image generator, you give it text, it generates an image, and so on. And then when you give it a request like read out loud the content of the image, here's again the chain of thought. It says, I will use the image captioner tool to caption the image, and then the text-to-speech tool to read it out loud. And here's the Java code, or the Python code. Okay? Here's another example. Read out loud the summary of that page, and this is the chain of thought, the explanation. I will use the following tools, blah, 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 to download the text, then to summarize it, then to read it out loud. And here is the code. And here's the result that you get if you run the code. So, and there are also lots of people who try to allow these models to also read images, not just text, and they become multimodal, foundational multimodal models. And this is where I'll probably stop. We only have, I think, 4 or 3 minutes for questions. Right? Maybe. And you can also talk to me at the next coffee break or whatever.
Okay, it's basically 2 questions. So far we've talked about natural language processing. And I wanted to ask something that was talked about briefly, if the same things can be generalized in code generation tasks, basically the auto-completion part. And the next part is regarding math and why sometimes LLMs are bad doing math.
I don't know why. I know that many people are trying to use LLMs to help them in mathematical proofs or planning, for example, right? Or even robotics. You can think of LLMs that don't just generate text, they also generate pieces of code that drive the arms of a robot, for example. So it's probably, yeah. Let's talk during the coffee break. I can tell you more. Yeah.
Thank you for your presentation. Very quickly, I'll ask my question. How safe is it to use a language model to create data and train another language model on it? Is it safe or no? Because I understand OpenAI had done it at some point, but it didn't really work.
Everybody's doing it. So I have students, and everybody's doing it. You need new training data for a new task. You ask ChatGPT, you prompt it, and you get artificially generated. You do data augmentation in a sense, but using LLMs. But then you need filtering mechanisms to filter out what is probably bad examples and keep only the rest. It's a loop. Right?
Could that result in overtraining sometimes if you used the same model, but you created a newer version through the older version model? The data that
usually nowadays one is stealing responses of one model to train another model, right? So if you inherit, I mean, you know, there's bias, there's all sorts of problems that you can also copy into your own model. Okay.
Thank you.